Chemistry and matter. That's what we're going to be discussing in this first lesson in my brand new high school chemistry playlist. We're going to be releasing videos weekly throughout the 2020-2021 school year, covering 16 chapters in what is typically presented in your average high school chemistry course. So whether you're in high school, whether you're being homeschooled, whether you're doing online school in the middle of the pandemic, I hope you find these helpful. And if you'd like to be notified every time I release one of these, subscribe to the channel and click on the bell notifications. And if you're interested in the study guides that go with these lessons or practice materials for the course, check out my premium course on chadsprep.com. All right, so let's dive right in and let's talk about what is chemistry. So chemistry is really just a study of the interactions between matter and energy. That's simply what chemistry is. And it's a very simple definition here, but it's much more complicated than this, right? So if you look, chemistry is often referred to as the central science. And what that really means is chemistry kind of connects biology with physics. And you'll hear some people say that biology is really just a bunch of chemistry when you look down into it. Things of this sort, or chemistry is the foundation of all biology. And that makes us chemists feel really good. Yeah, you biologists, you're just doing a bunch of chemistry. It's really all about the chemistry. So and there's some truth there, biology, the study of living systems and things of this sort. If you look at it at the molecular level, it's just a bunch of interactions and chemical reactions going on inside cells and things of the sort. And so biology can be reduced to a bunch of chemistry. But then the physicists come along and they say, yeah, but chemistry is really at its basic levels just a bunch of physics. And physics likes to look at everything in the context of 4 fundamental laws like gravity or the interaction between plus charges and minus charges and things of this sort. Well, it turns out the vast majority of chemistry really can be reduced to the interaction of plus and minus charges, which is really mind-boggling that much of it really reduces down to that simple principle. And so in a sense, chemistry really does reduce down to a bunch of physics. But we do study these disciplines separately, and we're going to study this chemistry, which kind of is right in the middle and connects the other sciences together. So chemistry is the study of matter and energy and how they interact with one another. And we can break it up into a number of different disciplines and stuff like this. And for a typical high school or college freshman course, you might call it general chemistry. But the truth is that's actually kind of a generic term for it. It actually would be called properly inorganic chemistry. But for inorganic chemistry to make any sense, we actually got to define organic chemistry first. And organic chemistry is a course taken on the path to med school and things of this sort, and it often is, got some wincing with pain associated with it as well. We call it OChem for short. And organic chemistry has nothing to do with like not using pesticides and natural best growing practices or anything like that. Organic chemistry actually is all about the element carbon. It turns out that the vast majority of living systems, the fundamental elemental building block of all the lovely macromolecules involved in living systems are all based on carbon. And so there's an entire branch of chemistry devoted to just looking at carbon-based compounds, and that's organic chemistry. And therefore, inorganic chemistry is then all the other elements. So the chemistry of all the other elements, that's inorganic chemistry. And you can take an advanced course in inorganic chemistry as like a senior in college. But when you're taking high school chemistry or general chemistry as a freshman in college, you're really taking a course in inorganic chemistry. Now, some of the other branches would be like analytical chemistry, which is really looking at chemistry as like kind of an analysis tool, like doing titrations to figure out acid content in a can of Coca-Cola or something like this. So as an analytical tool, so there's that. There's also what's called physical chemistry, and physical chemistry is a bad word, just so you know. So often called PChem for short. You'll see a bumper sticker here and there from different universities that says, I survived PChem, because it's that bad. So typically to take a course in physical chemistry, you've got to have Calc 1, Calc 2, Calc 3, a little bit of differential equations, and linear algebra wouldn't hurt as well, and maybe even some mathematical modeling software proficiency. All those would be very helpful. So it's very math intensive, a little bit of a pain in the butt of the course. Truly fascinating, truth be told, but very math intensive, and lots of students struggle with PChem. And then the creme de la creme of chemistries, at least in my book, is biochemistry. And biochemistry is the chemistry of living systems. It is taking biology and looking at all the way down at like the molecular and atomic level. And it is fascinating. When you look at a little cell, so that all living things are made up of, that cell is actually a ginormous city. And there's factories in this city and things of this sort, and there's information processing going on in the city. It really does look like a little city when you look at it at that molecular level. And that study is actually what we term biochemistry. And for me, that's that's actually the most fascinating part. Now, I like inorganic chemistry and I like organic chemistry, but I love biochemistry. It truly is fascinating, mind-boggling when you see the complexity and the beauty going on inside each and every living cell inside your body. So now we're really ready to begin this first lesson in high school chemistry proper. And to start this off, we got to talk about what's the matter. Wait a minute. Wrong question. My bad. That's psychology. What's the matter? What is matter? That's the question we're looking at, and that's not the last lame joke you'll hear. So what is matter? We talk about chemistry as being the interaction of matter and energy, and you probably have a little bit of idea what energy is, but what in the world is matter? Well, simply put, matter is anything that has mass and occupies space. That's our lovely working definition. So has mass. Now, mass is a little bit of a technical definition, but we'll kind of liken it to weight for the time being. As long as you live on the surface of the Earth, you're probably going to encounter mass and weight as being equivalent. Now, because all of us, or almost all of us, spend almost our entire lives or our entire lives on the surface of the Earth, why wouldn't we equate them? Because if you go to the moon, you'd actually see a difference between mass and weight than how they were defined on Earth, things of this sort. But for now, we're just going to liken it to weight. It's definitely very related to weight, but not quite the same thing. We'll see a better definition a little bit further down the road. But matter is anything that has both mass and occupies space. So that's matter. And if you look at it at the fundamental level, all of matter, if you get small enough, is made up of these little spheres, at least we like to model them as spheres, so called atoms. And these atoms come in 118 different types, and those 118 different types are just types of different elements. So these little atoms, these little spheres, are just different types, and these different types have different masses associated with them, different sizes associated with them, things of this sort. And basically we can take all sorts of different combinations of these different types to make the different substances, compounds that exist in the universe and things of this sort. This is our study of chemistry. Again, it's matter. Has mass, occupies volume, and at the fundamental level, the basic building block of all matter is going to be the atom. And these atoms come in 118, at least. That's our current count. They keep discovering new elements, but we're kind of reaching somewhere near the limits. But right now we've got 118. At the time of this filming, that may grow a little more over time. Now, in any discussion of matter, we've got some vocabulary we use to describe the different properties of matter. And so it turns out there's two fundamental types of properties for matter. There are physical properties and there are chemical properties. And if you change one of those physical properties, we'll call it a physical change. And if you change one of those chemical properties, we'll call it a chemical change. And so we got to talk about what these physical properties are. So a physical property is simply something about the physical nature of the matter you're looking at. It could be the shape, it could be the color, it could be the size, things of that sort. And most commonly, one of the big ones we like to talk about in chemistry is what phase of matter you have, or sometimes what state of matter. And the three most common examples of that are solids, liquids, and gases. And I will assume that you actually kind of have a general idea what a solid, a liquid, and a gas are, but we will explore those different phases in quite a bit of detail later on in this course. Now, a chemical property, on the other hand, doesn't necessarily deal with kind of the physical features of it, but the chemical behavior. And so the chemical behavior deals with like undergoing chemical reactions. And so when substances undergo chemical reactions, big thing you should realize is it produces new chemical substance. The chemical substance you start with is different than the chemical substance or substances you end with when you undergo a chemical change. And the properties associated with those chemical changes are called chemical properties. And so good example of this might be like flammability. And so flammability is a chemical property, how flammable something is. And the reason that is because burning something is actually a chemical change. When you burn something, you're actually combining it with the oxygen in the air around you to create new chemicals that you didn't start with. So you're taking whatever you're burning plus oxygen and creating new chemicals. And because they're changing their chemical identity, that's a chemical change. And so we might call combustion or burning something a chemical change, and the property associated with that might be called flammability. Now, if you look, there's another example on there of a chemical change. We've got oxidation, and oxidizability might be the associated chemical property. Now oxidation is something we'll cover a little bit later, but it involves the loss of electrons, which we haven't even talked about, which is why we're not going to really dive into it. But I did want to provide you with a second example there. Now, Again, physical properties and physical changes, we talked about, shape and color and stuff like this. So if I take this lovely study guide I'm doing here and rip it in half. So in that case, that is a physical change. I've changed like the shape of it and the size of it and stuff like this. But the paper here is made of cellulose, and that chemical identity, still being cellulose, has not changed. So that is not a chemical change, just a physical change. All right. Let's get this lined up again. Cool. So some of the physical changes then, if a state of matter or a phase of matter, solid, liquid, gas, is a physical property, well, again, changing the phase of matter would be an example of a physical change. So when I turn a solid into a liquid, when I melt something, or turn a liquid into a gas when I boil something, those are examples of also physical changes. I'm not changing the chemical identity of a substance, I'm just changing the phase of matter in which it exists. Other examples might be like salt dissolving in water. It turns out when salt dissolves in water, you still have salt and you still have water. Their chemical identities have not changed, and so we classify that as a physical change. And I want to bring that up in particular because it's a little bit of a tricky example. Students are often kind of coerced into thinking that maybe that's a chemical change, but it turns out it's just a physical change. No substances have changed their chemical identities. So another example I want to bring up of a chemical change, and it actually goes hand in hand with oxidizability, and that's when like a nail or a piece of iron or steel rusts. And it turns out it's actually combining with oxygen to form a new substance, iron oxide. So iron combines with oxygen to produce iron oxide. So your starting substances and your final substance are not the same, and that's evidence that a chemical change has taken place. So something rusting definitely turns out that's an oxidation, it turns out, and definitely an example of a chemical change that commonly shows up on a chemistry exam. All right, some more vocab here. We've got to talk about elements and compounds. And typically, if you've got any substance in the universe, it's either an element or it's a compound. So any single substance. So if it's an element, it's really just a sample that contains only one element. So all the atoms in that sample are just going to be the same element. So you can have essentially, I've got several examples there. Let's say pure sodium metal. And so it turns out sodium metal, it is a metal, but it turns out it's got a kind of a weak consistency, and you might be able to, if you got a sharp knife, slice it like butter. Not quite the consistency of butter, but you'd be able to slice it with a sharp knife. Things of that sort. That's pure sodium metal. You might also have other examples put there are like silicon or hydrogen, and I also put S8, a more complicated one. So it turns out that some of those elements, instead of coming one by one in a sample, it turns out they form what are called molecules, combinations, where they come two by two. So like hydrogen here, and hydrogen's an example of what we call a diatomic. And you're supposed to actually know those 7 diatomics. So I'm going to introduce them here, but you will see them again somewhere along the way. And so there are 7 diatomics, and conveniently enough, on your periodic table, 6 of them form a nice outline of a number 7. So if you look, you got nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2, Br2 for bromine, and I2 for iodine, and they form a nice number 7 on the periodic table. And then hydrogen is the 7th one. And again, as a typical student, you're expected to know, oh, most of the elements come one at a time, but those 7 come as diatomics, and they come 2 by 2 by 2, and we use that little subscript to identify that. Cool. Some people use a little mnemonic here to memorize that as well, and they say never have fear of ice cold beer or something along those lines. And personally, I like just looking at a periodic table and seeing the number 7 because you're always going to have a periodic table in front of you. So you got one in your textbook, you'll see them on the walls of classrooms, you'll see them on socks, you'll see them on ties, you'll see them on tattoos. It's terrible. So, but odds are you are going to have a periodic table accessible at all times. And so if you can look at a periodic table and identify where those 7 diatomics are located, great, help you memorize them. Cool. It turns out there are some that are like sulfur here that are even octatomic here. So that's kind of a rarity. There's not like a bunch of these. I can't name another one for you. It just turns out like the most common form of sulfur is octatomic. That's not usually something we make you memorize. I just want to make you aware that coming 1 by 1 or 2 by 2 is not the only option, but they're by far, hands down, the most common options. So those are elements. Now a compound is still a single substance, but it is made up of multiple elements. And so if you look at the examples on your handout there, so here we've got carbon dioxide, the same stuff you're exhaling right now along with me. So, and it's a combination. It's a single substance, but it's got carbon and oxygen combined. And it turns out it's in a set ratio, a 1:2 ratio between carbon and oxygen atoms. So, but it is still made up of multiple different types of elements as a single substance. That's what a compound is. So some of the other examples I put on there are sodium chloride or sodium bicarbonate. So water's another example. Not on your handout, but we'll stick it up there, H2O. So any one of these is a single substance that's made up of more than one element. And it could be two elements like these three, or it could be like four different elements like sodium bicarbonate there and stuff like that. So, but again, all examples of compounds. Well, let's move on to the back side of this page. So the next bit of vocab we've got are pure substances versus mixture. And so again, any substance in the universe is either going to be an element or a compound. And so a pure substance is any single element or any single compound. So if you look on your handout there, so we've got O2 here, and I specifically said O2 gas, which we often represent the phase of matter here with a little S, L, or G in parentheses to represent that solid, liquid, or gas. So here's O2 gas, and it is just a single element. It's diatomic, and that doesn't matter. It's still just one type of element here, oxygen. And so that's a pure substance. It's a single element. But it could also just be any single compound as well. And so notice the next one on there, I've got water. And as long as it's not got anything other than water present, that's a single pure substance as well. So any single element or any single compound, that's a pure substance. Whereas a mixture just has to have more than one substance. And that could be more than one element, like you see in air. So the air you're breathing right now is like 78% nitrogen and 21% oxygen. So mostly a mixture of two diatomic elements. Now technically there's a little bit of carbon dioxide in there because you're breathing that out, and there's trace amounts of other gases there as well. And so the truth is not just really two elements, there's also a compound in there, and there's even a couple of other elements and compounds that are, again, present in really trace amounts in air. But air is a good example of a mixture because it's not a single substance, it's at least three substances plus even a few more. Another example would be salt water. Let's write that proper. So salt water, it has both salt, which is sodium chloride it turns out, and it has water. And they're combined together. So they're mixed together. Even the way we use that kind of belies the fact that it's a mixture. But you've got more than one substance. So in this case, it's two compounds. In the example above, it started out as two elements, but then even a third compound was in there. But it doesn't really matter if you've got two elements or two compounds or one compound and one element or more than even two substances. As long as you've got two or more substances together, that is now a mixture. So if you've got any one element or any one compound, that's a pure substance, but two or more elements or compounds, that's now a mixture. So now that we've identified mixtures, the next bit of vocab talks about the two different types of mixtures. And we've got homogeneous mixtures and heterogeneous mixtures. And you might already know that the prefix homo means the same and hetero means different. So, and that's kind of at the heart of the definition here. So a homogeneous mixture, so has uniform or the same composition throughout the entire mixture. Whereas a heterogeneous mixture has a different composition throughout the mixture. So again, a mixture means you have more than one substance, and the question is it uniformly mixed? So it means if you take a sample of that mixture, anywhere you take a sample, if it would have exactly the same composition of the different components in the mixture, well then that's going to be a homogeneous mixture. So a good example here would be milk. So when you've got a lovely bottle of milk, oftentimes you'll even hear it called homogenized milk, right? And so it just belies the fact that it is a homogeneous mixture. And so no matter where you take a sample of that milk, the different components that are present will always be present in exactly the same composition. That's a homogeneous mixture. Another good example would be salt water. Sometimes, because we're going to find out when we get over to heterogeneous mixture here, I'm going to put salt water over here as well. And so sometimes salt water, mixture of salt and water, can be a homogeneous mixture, and sometimes it can be a heterogeneous mixture, and you definitely want to understand in which cases is it one versus the other. So again, we're going to heterogeneous mixture here, and here this is now a mixture where you do not have a uniform composition throughout. And the simple example I'll give you is a pizza. So let's say I give you a supreme pizza, and are you guaranteed to get a piece of pepperoni in every bite, or an olive in every bite, or a sausage in every bite, or a green pepper in every bite? No. Some bites you'll get green pepper, and sometimes you won't. Some you'll get an olive, and some you won't. The composition is not the same throughout that pizza. So that's a good example, kind of, big macro example, non-chemistry example of a heterogeneous mixture. Now, one other way to kind of distinguish these is usually if you've got a homogeneous mixture, it might be actually difficult to tell that you even have a mixture. So oftentimes you'll see this used very commonly as a solution. So, and a solution is usually a mixture between a liquid and some other components in it, and you can't tell even necessarily that there's other components in that liquid. And so a solution is definitely by far the most common example of a homogeneous mixture. Now, a heterogeneous mixture, you can totally tell that you've got multiple components in there and stuff like this. So if you look on your handout there, we've got vinegar oil salad dressing. That's a great example. Now, if you've got vinegar oil salad dressing, so note that the vinegar is dissolved in water, but the oil is a whole separate layer. And notice, let's say you just take a bottle of vinegar oil salad dressing and you take a straw and you sip it, take a little sip from the top, and then you put the straw all the way down to the bottom and take a little sip. They're going to taste very different, those two samples. So because in one, you're going to get more of the vinegar side of things, and one, you're going to get more of the oil side of things. And that's why every time you want to use that vinegar oil salad dressing, you got to shake it up really good to make sure it's mixed. But notice what happens as soon as you stop mixing it. Well, those two layers separate back out. And that's one of the hallmarks, or one of the ways to kind of identify a lot of heterogeneous mixtures, is that they will separate out and form, separate layers. And that's definitely an evidence that you've got a non-uniform composition throughout the mixture and stuff like that. Can of paint would be another good example. And for the same reason, if you notice, when you go down to Home Depot or Lowe's or something to buy some paint, so they put it in this big fat mixer, and it's going to stay good and mixed for a little while, but even then you still got to take a stirrer home, and once you open it, stir it real well, because just like the vinegar oil salad dressing, it likes to separate out the different components that are in that paint because it is a heterogeneous mixture. And so before you use it, you got to mix it up, because as soon as you stop mixing, it will slowly start separating back out. Again, betraying the fact that it's got a lack of uniformity in the composition. Cool, so let's go back to that salt water example now that we've got listed under both. So turns out salt's pretty soluble in water. That means you can put a whole lot of salt in water and it'll all dissolve, but only up to a point. And again, you can put a lot of salt in water at most temperatures and get it all dissolve. Now, as long as you're got all that salt to dissolve in the water, that's going to be an example of a homogeneous mixture. And it turns out when you reach that maximum level that could possibly dissolve, we call that a saturated solution. And before you reach that point, we'll call that an unsaturated solution. So if we've got salt water, and it's what we say unsaturated, so there's no salt sitting on the bottom or anything like that, it's all dissolved, that would be an example of a homogeneous mixture. However, if you go past the saturation point and keep adding more salt, all that could be dissolved in the water has been, then when you keep pouring more in, it actually will just sit on the bottom. This happens with sugar as well, and if you eat Cinnamon Toast Crunch, you know this. So when you get to the bottom of a bowl of Cinnamon Toast Crunch, there's just sugar crystals all over the place. That would be another example, sugar mixed with milk and not dissolved completely, of another heterogeneous mixture. So the same thing can happen in salt water if you've got some salt on the bottom. So if you've added so much salt that you still got some crystals sitting on the bottom, that is now an example of a heterogeneous mixture, because you've got a certain amount of salt in the composition of the liquid part, and then you've got a greater amount of salt down below, and so you don't have a uniform composition. Again, good example of a heterogeneous mixture. All right, the last little bit of vocab here is intensive versus extensive. And these are descriptors of properties. You can have an intensive property or an extensive property for matter. So, and it really all comes down is, does the size of the sample of whatever substance you have, does it matter? Does the size of the sample matter? So if the size of the sample doesn't matter, then it's an intensive property. So, however, if the sample size totally matters, then that's going to be an extensive property. And so hopefully this, I shouldn't say hopefully, but this probably seems a little bit vague right now, but we'll definitely make this concrete. And so a good example of an extensive property might be something like mass. And so let's say I've got like a glass of water versus a whole swimming pool full of water. Well, one of them is going to be far heavier than the other, the swimming pool full of water, and will definitely have a greater mass. And so the size of your sample totally affects mass. Mass is an example of an extensive property. So lining right up with that would be volume. And volume is pretty much how much space a substance occupies, or your sample occupies. And again, the swimming pool full of water has a much greater volume than the glass full of water. And so volume is totally, again, another example of an extensive property. Now, intensive property, again, is a property that the sample size itself does not matter. And a good example of this would be melting point. And so the melting point of a substance is just the temperature where it undergoes the phase change from solid to liquid. And for water, this occurs at 0 degrees Celsius or 32 degrees Fahrenheit, but we'll use Celsius a lot more commonly in this class. So 0 degrees Celsius, that is the melting point. And it turns out it doesn't matter if you have a glass full of water or a whole swimming pool full of water, it's gonna undergoes that phase change from solid to liquid at 0 degrees Celsius. And so any of your phase change temperatures, those are good examples of intensive properties. So, but I want to put one other on here that commonly shows up in this context, and that's density. We'll study density in a little more detail here in the next chapter, but technically density is simply the ratio of mass to volume for a substance. So it turns like if you have water, it turns out that 1 milliliter of water weighs 1 gram. And so we'd say it has a density of 1 gram per milliliter. And those units shouldn't make a whole lot of sense now, but it turns out that it doesn't matter if you have a glass of water or a swimming pool full of water, its density would be 1 gram per milliliter in either case. And this is not very intuitive here because mass by itself is an extensive property. The size of your sample affects the mass. So volume is an extensive property. The size of your sample affects the volume. But when you take the ratio of mass to volume, that is not affected by the size of your sample. So again, that's not intuitive, and you definitely want to file away that density as an example of an intensive property. So often on an exam here, you're going to get questions that involve identifying whether a property is intensive or extensive, as well as possibly just simply knowing the definitions. And density is one that shows up really commonly because it's not intuitive. So one thing you'll find out about chemistry teachers is they'll tell you that they're not trying to ask you trick questions on a test, and they're lying to you, just so you know. And so as a common question, they'll throw density on there because it is a little bit tricky, because mass and volume individually are both extensive, but the ratio of mass to volume density is totally intensive instead. Cool. And this is the last little bit of the vocab in this chapter for the descriptors of matter. So hopefully this lesson on matter at least makes a little bit of sense, but you'll find out that you need to reinforce it with some practice. So whether you've got a good textbook or something like that, or you can check out my premium course on chadsprep.com, plenty of practice materials in there, but you definitely want to reinforce this with some practice. You'll find that chemistry is a lot like a math class, where the real learning doesn't come when you like read a textbook or even watch a good lecture or anything like that. The real learning is going to come when you do some practice.